We're going to be covering logic gates and how they process binary signals. What do you need to know before you do this? Well, you should really have some idea of what binary is, and the other aspects within this topic that are not quite so important is you don't know how to actually store numbers in binary, and you don't need to know how to store text, so those two won't be required from the topic heading, but what binary is will be. And so what are you going to learn today? I'm going to teach you what a logic gate is, the different types of logic gates, that's AND, OR, and NOT, how to draw logic gate diagrams, and how to construct truth tables, which are numeric representations of the inputs and outputs from logic gates. So to start with, we're going to look at what is a logic gate. Well, a logic gate is essentially a component of a circuit. It's a device that can input one or more electronic signals, and it will then process it and perform some logical operation on it, and then it will output the results of the operation on those signals. So let's give an example of that. Here's the symbol for an AND gate. Of course, they don't look like this in real life. They would look like a simple chip. Often the process will be embedded well within a chip. And the AND gate takes in two signals, there being signal A and signal B. A signal is an electrical current, and if there's a signal present in both A and B, then the output Q will be that there's an electrical signal there. And so let's look at a truth table for this. What this has done is shown all the values for AND and all the values for A and all the values for B. And so it's all the different combinations there, A being off, off, off and B on, A on, B off, and A on and B on. And you'll see that Q is only on, as in a 1, when both A and B are on. The next gate you should really know is the OR gate. This takes an input A and an input B, and if either of the signals A or B have a signal there, or both of them in fact, so if there's a signal at A and there's a signal at B, then Q will be on. Let's look at the specifics of that. So we've got these signals here, A and B, and if there's either of them are on, so either are on around here, then then Q is on. Finally, we've got this NOT gate. NOT is the simplest of the gates that you need to learn about, and what it simply does is if A is giving in a signal, then Q won't have a signal, and if A doesn't have a signal, then Q will have a signal. So it's a very simple truth table there. So if A is 0, then Q is 1. If A is 1, then Q is 0. So let's take an example of this and look at a situation whereby you require A and B to be on, or C to be on. So maybe you're thinking of a burglar alarm system, that if both the door has been opened and there's somebody standing on the map, or there's been somebody detected using an infrared beam, then you'd like the alarm to come on. So that's A and B or C. So both A and B are on, or if C are on. And so the first thing that we do is maybe draw up a truth table for this diagram. So we've got the AND gate at the next taking in A and B, so that's A and B, and then we've got an OR gate after that taking C and giving the output. Then we'd like to construct a truth table for this scenario, and so I'm going to look at this truth table for a little while. And so to start with, I draw out A, B and C and go through all the different values. So you'll see here I've gone through every single combination of A, B and C. I then look at A and B and draw the truth table for A, and you'll see that A and B is repeated here and here, and so only when A and B are on does A and B equal 1. And then finally we combine this column with this column and do an OR function on that. So these two are looked at, and we said if either of them are 1, then we'll write 1 here, and we'll see the only instance where either of them are 1 are these ones highlighted here. And so that's how you do A and B or C. We're going to look at a slightly different example now, and we'll notice that we've just flipped around the and or, and want to see if they're equivalent. So is A and B the same? A and B or C the same as A or B and C? We'll probably find that they're different. So A or B and C. So either A and B are on, and C must be on in order for a signal to happen. And so this way we've just flipped them around. First we've got A or B, and then that's combined with the C signal to be A or B and C. And then finally we produce the truth table where we go through all the different options. And so here we say A or B. So A or B, is A or B on? No. Is A or B on? Yes it is. Is A or B on? Yes it is. A or B, well both of them are on, so that means that A or B are there. And the same happens in the second half. And then I examine the two tables together and put an and on that. So if either of them, I need both of them to be on for the A or B and C to be present. And only in these instances are both of them on, and therefore only those ones return true. And then if you compare that to two functions ago, you'll see that this table, A and B or C, is not equivalent to this table, A or B and C. So those two things don't mean the same. And that's why subtly in a natural language you might get mixed up with your ors and ands, but by expressing them through a logic circuit and a truth table, you can make them make your logic much more precise. We'll look at two more examples. Example 3, so only got two inputs this time. A and not B. So if we look at the logic for this, so not B is dealt with first, so we convert the B to a not of what it is, and then you combine it with A to produce the output. Look at the truth table, you've gone through all the options of A and B. Then you look at, you inverse B, so where B is a naught it becomes a 1 and vice versa, and then you combine the two together and say when you have A and not B, and that's in this instance here. And then finally we can look at not A and B, and so first of all we inverse the and because it's a not A, so we inverse A with the triangle symbol meaning not, and then we combine it with the B, which is this big D, and when the two come together we'll produce a truth table for that, and you'll find that the one is not equivalent to the other. A good way to experiment with this is to use a logic gate simulator called Logically. That's found at logic.ly, and you can click the try it now and an applet will open hopefully on the screen. Oops. And you can click try online, and that will download an applet of which you can experiment with and produce your own logic gate diagrams. A nice project that you might want to consider is adding two binary numbers up using the logic gate simulator. It takes a little while to load. There we go. And so this will present you with a range of different logic gates that you can drag and drop into the screen and then see what the outcome was. So if we look at one of the ones that we did before, we did not A and B, and you can place switches to choose your inputs, and you can place a light bulb to show your output. So here I'm dragging and dropping into the screen, clicking the symbols together, and then we can go through all the different options for A and B. So this one being A is now on, not on, and on, and that one's off. So that's a good way of learning how to use logic gates. And so finally, just to review what you've learned today, you've learnt what a logic gate is, the different types of logic gates. I've shown you how to construct logic gate diagrams, and we've also had a go at constructing some truth tables which basically go through all the different values of logic gates.